Du sagst wenn. Okay. Yeah. Okay. Right, welcome back, or in case of people online, welcome. So this next part is a slightly longer talk for us here, but in particular, it's also a talk that's also at the same time happening on GReTA. GReTA is a graph transformation community, international sort of seminar on diverse topics in graph transformation. We always meet on the Friday at this time regularly for various talks, and it so happened that a talk was scheduled for the same time that we felt was also relevant to this community, and so Patrick's kindly agreed to give it as at the junction of both times, but hopefully for the union of participants and understanding. And so I'm very happy to have Patrick Stünkel here with us, who will talk about the software interoperability and solutions for that. And I shall hand over technology to him. And the floor as well.
Yes, thank you very much. Important with sequential speaking right now. So thanks, first of all, thanks very much for being here and giving this keynote kind of, that is called a keynote. It's a bit surprising. And I think, yeah, it's very nice to be here. And first of all, a little bit disclaimer. First, this was planned, as said, for the graph transformation community. And then I was spontaneously asked if I could also give it here. So I said yes, because it's great to have a bigger audience, but it's also challenging because now I have to please a lot more people. And I don't know if I will manage. So there will be a little bit of everything, and there's probably not enough of each. But if you're interested, you can send me an email afterwards, and I'm probably also happy to give a detailed talk about some of the topics later, maybe in GReTA or in this occasion. Okay, first of all, since it's also a little bit introduction of myself, a little bit about myself. So I just happened to be very recently become an associate professor at HVL. So now I also have time to continue in research in academia. That's great. And just before that, I was working when I finished my PhD. So I thought like, okay, I'm a doctor, so I guess I can start working at the hospital. So that's when I did a short detour into another interesting topic where I did in pathology, where I looked into how we could combine process mining with process modeling, and then to do some kind of digital twins to do optimization that people get their specimen answers quicker. So that's another topic I'll not talk about today. And before that, I was doing my PhD also at HVL about the topic that will be today. And before that, also a little bit interesting probably for the GReTA community, because before that, the non-ASCII character in my last name probably identifies me pretty clearly as German. So I was in Hanover, and there I studied at a small University of Applied Sciences under supervision of Michael Löwe, who may somebody know, who unfortunately passed away in 2019. And he is a bit like one of the first big figures in when it algebraic graph transformation started back with the single push out approach. Yeah, just a little bit about that. So the background of today will be this interoperability. So first of all, what is that? So I just took the definition from the IEEE glossary because I think it fits pretty well. Just like some systems are able to exchange information and then can also understand what was exchanged and process that further. So I guess that's a pretty broad and nice definition. And usually people split it up into levels. And like this, the resemblance with probably the OSI networking model is intentional because it nicely like splits it up that you have different aspects that you have to address. So on the bottom, you have like communication itself. So that's OSI levels 1 to 5. Then on the top level, you have laws and organization and all these things that's more social science. And then software engineers are very happy in the syntactic level because you can invent your new serialization format, your new messaging system, and so on. But today, the focus will be on the semantic level. And there you deal with domain entities. And I guess that's like the prime domain of model-driven engineering. So what's the problem there? So every time you have start and you have this conceptual idea about something, and then okay, you agree on the term, and then when you start modeling in your head, there's easy you diverge, and then you make it more concrete, so it's actually technically implemented like database schema, and then it will diverge. Even a concept like person having addresses can be different modeled in different ways. Should be last name, first name, separate attributes? Should the attributes be like structured fields, or should it be a list of strings, which are the lines in the address, whatever? So already a simple concept has many degrees of freedom. And the ways you can address this is standardization. Okay, you force this is the way we do it. That's like the modernist approach. There's one single truth. Or you just, okay, you accept that there will be deviations and you try to mediate that by translating, usually. And that's like the postmodernist approach. And both approaches have their back and forth, nicely summed up by an XKCD comic each. So standards have to tend to proliferate, and it's probably there will never be the domain model of everything, because to agree on that would be very tricky. And with the other world, it's like, okay, you always have to carry around all this adapters and dongles, and sometimes they don't work. So yeah, and I mostly focus on how do we address that mediation, basically. So I picked out some example problems, and I will convince you that they're basically the same. So most of the MD people in this room knew. So you have many stakeholders working on different aspects of a bigger system. They all have their favorite tools, and which are the best for the certain use case. But yeah, but you start up modeling some aspects of the system from different angles, and it's easy because you always work in your isolated box in your tool, and it's easy to not see everything that you start producing an inconsistency. That's one of the use case scenarios that I address. The other one is every time you have a service-oriented architecture, when you have many systems, they have different interfaces, system interfaces realized by different technologies, but they somehow exchange entities that are the same. So like if you have a hospital and you have some treatment process, you have the patient information that travels through many information systems. And there's also inconsistencies that can arise. And that said that you can somehow consider them as the same problem in this MDE world, which some people might not like it, but it's a nice concept, this meta-leveling hierarchy from the MOF, where you have like data on the lowest pattern, and then the models describing that, and then you have the model of the language, and then the model of how to make modeling languages. And you can fit actually the two scenarios in here. So the collaborative example that I show first, that will be there. You have the levels, you have different modeling languages and different models. And the other one would be the level there. So you have data models and you have data that you kind of mediate between. So you can think of them in the same way or similar way. And of course, this problem has been touched on by many disciplines, and this is just a very short whirlwind tool. So I will not cover every aspect, so don't feel offended if I leave it out. This is just a very short overview that some of the areas that are relevant to this. So, and they touch different disciplines. So of course, the whole problem itself, it's older than me. So in requirement engineering, the work of Steve Easterbrook, and so this viewpoints system that they started working with, was one of the first mentions, or at least one of them, that you have like, okay, also people model a system from different viewpoints at that point, and then yeah, inconsistencies can arise, and you have to somehow deal with them in some bigger framework. They were dealing with that on a logical, so your models were like, and then encoded into logical statements, and you can merge them and see then if there's inconsistencies. So the whole thing, inconsistency management. In the UML, you find that also because UML is basically just a collection of languages where you model a system from different viewpoints. And yeah, you can also, there are inconsistencies can arise between a sequence chart and yeah, state chart and so on. Yeah. So then there's this other domain, which maybe not so many people might know, but people that work with bidirectional transformations pretty much know, is this lenses idea. This comes from databases where you have a source database and you make a view from some tables. And then you can always, of course, from the source derive a view, but in what situations can you propagate from the view back to the source? And then they formalize this in something called a lens. That means the get goes from the source to the view, and then you have a put operation that when you know the old source and the new view, you can combine them. And there's a whole bunch of theory about this, and especially in functional programming, where you can make laws and proofs about this, that your get and puts are correct. And there's a whole bunch of unification using category theory about that topic. And then going next to this, a bit more to MDE again. So model management, this idea is also quite old. So the idea is that we are pretty familiar with everything is model. These are the atomic assets, and we can do something with them. We can merge them, we can match to find their links, we can verify if they're consistent, and so on. And actually, MDE wasn't first. It was actually databases were first. So there are some old tools like Clio, Rondo, where they basically did this for SQL schemas and XML. And but then it also come into the MDE community. So Epsilon is probably one of the big known families of languages that you can use for modeling. But there are also others. You have Gmorg, and you have the ones that they do in Toronto with this modeling. But the idea is you have models, and you have somehow correspondences between models, and you can do some operations on them. And again, you have this idea of, are things consistent, and how to make them consistent again. And then finally, to have like this is for the graph transformation community. So when you talk about model management, synchronization, and transformation, mostly people think, triple graph grammars, because this is basically how you do it. So the whole idea dates back to Andy Schuer's paper from '94. And the idea is you have some languages. You maybe have the language of classes and object diagrams, class diagrams, and you have the language of database schema, the classical OM, the hello world of model transformation. Right, so you can, of course, relate some concepts from one language to the other. So you have classes that correspond to tables, you have attributes that correspond to columns. And the nice thing, or this news nice, you say how both structures evolve consistently together. So that means I can, when I found a table belonging to a class, then I can add an attribute here and the table here that somehow belong together. And then the big formal trick is you can split that up. So if I detect I added an attribute, then of course I have to propagate that I also need to update the table. So there's a whole machinery of theory and also tools to how to do this consistently. And some people, they also said this is like a delta, they put it also in this lens framework. But my main point here is that this is binary. And binary is not enough. Why is that? So there's this nice example, which I got from Zinovy is, so assume you have 3 class diagrams, and then you want to check if they all consistent. And if you only have binary means, so you can always compare 2 at the same time. You can compare A and 2, then they are consistent. I compare these 2, they are consistent. I compare these 2, all consistent. But only if I merge them all together, then I see that my class inheritance is a cycle, which is not allowed. So that's why this is not enough. And it dates actually back to philosophy. There's a Pierce reduction theory, so that's pretty old. And here's some kind of there's some theory that there are ternary relations you cannot represent by binary relations. So this is the main motivations basically for my PhD when I say we want to do multi-array consistent model management. Yes. So, and then also some classification, how you represent this. So basically, I found out there's in literature, you finally found there's 4 approaches. You do it by merging, or you don't merge, but you have some kind of links that would be the weaving, or you do it operational. So you have transformations that have these links implicitly, or you extend your local models with information from the global scope. So can classify them. So that to the background. And now, so the main contribution in the theory. So, and this was something called comprehensive systems, and this is the topic the talk. So the whole thing is kind of distributed in a series of 3 papers, which are listed here. So, and they have some nice theoretical properties. So we'll get to them. So first, as a motivation, I have this, coming back to this modeling idea. So I have this model some kind of process like a patient referral. So maybe have a BPMN modeling language. I have a UML class diagram, and then I also have some decision tables. So they are not in isolation. But what you usually want to do, except what you do on a whiteboard, you just draw a link. You just draw this thing here has something to do. And maybe you usually attach also a rule that says this, okay, for example, the data objects that flow around my BPM diagrams, there should be a class for that. Or the decision, that if I have an XOR gateway, there should be a decision table for that, and so on. So I want to do this. And actually, I'm not alone with this. So we find many papers doing that. And it's basically what you do in triple graphs is what you do. So you add this thing in the middle. Okay, so we have this. So what we have basically models, and we have these links in between. And we want to somehow formalize this. So let's do one more step. And we just, okay, what happened here? Well, first of all, we remove the concrete syntax. So everything becomes boxes and arrows. And so for the formal people, this is a graph. Because, yeah, this is the main things you have. And we also actually have this colored thing in the middle. So now everything of these links or tentacles that you draw on the whiteboard, they also become boxes. And the tentacle acts, the ends that we had before, they also become something. So, and if you're in the work of theory and graphs, so there's something called, you can think about graphs, and you can think about mappings between graphs, which are called homomorphisms. And together they form something called the category. That's just both things set together, and then that you can compose the mappings, basically. Yeah. So these things in the middle, they are the mapping. These are graph homomorphisms. And important is that they are actually partial, which is the big difference between the triple graph case, where you have a middle structure that always has something here and something on this side. But when you have the multi-array side, so you have many possibly, you only relate concepts from 3 of them or 2 of them. So not every general concept that is overlapping might be represented everywhere. That's why you need sometimes it's undefined. That's the partial mapping idea. Yes. So coming zooming out a little bit again. So if we have models and we have meta models and we have constraints on them that we know, that's the local case. For this, we have tools. So now, and we can formalize actually this, because usually we say these are graphs or pre-sheaf topos for people who know what that is. That's where graphs, where you can basically have edges between edges and a bit more fancy structure. And on the bottom, we have the type, this instance of is basically also a morphism, because every model element, you assign a class in the meta model, a type, basically. And this typing is also a graph morphism. So this is how you formalize the normal, and you have something also for people. The constraints can be modeled as something like a predicate that says, because graphs representing a meta model as a graph is usually not enough, because this basically says the structure, but you usually need something also. You don't have multiplicities, for example, that you say this can only point to so and so many of this type. So for this, you need some kind of a predicate. That's something attach like a label, you attach on them, and that says on the instance level, it has to conform in a certain way. So this is set. So now we come to the multi-model world where we basically have the stuff on the left, but we have the new things where you have these links and we have consistency rules. And now we look for something, what is the formal structure that I can, what would be a foundation where I can put all this together? That's one of the motivations for CS. Yes. So first of all, one idea would be, when you have, how do I know that I have the local structures and I have theory and tools for that. And now I add these tentacles on top that connect models. And I want to have something for that. So I can say, we just map it below again. So we just go back and push it down to the level below, where we say, we can do it in models. And the general idea to do this is merging. In category theory, you call that co-limit. You merge everything together on one. And the diagram that you use for the co-limit is the things that say what is the same. So yeah, it looks like this. You take all the elements that look the same and you connect the arrows correctly. And then that's how you can do it. The problem with this is if you only look at this, you lose what does it come from. If you don't know, again, explicitly say what was the origin of element. And it only fits really if you have things are the same, but not every traceability link means these things are the same. It can also be, say, refers to or is built on top of something. So yeah, another theoretical aspect is that sometimes things can be locally inconsistent, but when you merge them, everything suddenly becomes consistent again. So yeah. For example, when you have some class diagrams and you have in one way you say like at least one or more B targets or at least one B target, and you look at the instances which are now on the right side, and they don't fit, but you somehow identify some elements that when you merge everything together, they have exactly one, which will be globally consistent. But when you look locally into the models in your editor, they wouldn't be consistent. So there are some issues with the merging. So the objectives were also, when we started, we want to handle multi-array. We want to have this idea of weaving, adding traceability links, somehow formal. We want to avoid the merging and somehow have this formal foundation. And some theoretical assumptions were like, we have these graph-like structures, we have morphisms that are the mappings, and we know basically if in the world of local modeling, we have tools and consistency verification. So it would be good if we somehow can come back to that. So, and then we came up with something that is called the comprehensive system, which is, this is the most theoretical thing today. So, basically so you have something called B that can be an algebraic signature with unary operations only. Think of it as directed graphs. There, the B would be just, you have two nodes, V and E, and you have the source and target mappings that say, so you have basically two entities, edges that will be mapped to the links. And then you have the vertices mapped to the set of nodes and things that say like, where do you map the edge ends? But you can think about with more complex structures. So you take this as an index and then you can define something set-based. So this will be just an algebra. So this is something like a local model. The only special thing is in the middle, you have some kind of this C things, the commonalities which map things. So if you remember the diagram again, in the middle there were some nodes that somehow relate stuff from the individual sets, and these mappings are partial. So a little bit more. So they form a category. So another concept. So you can make a diagram that looks like this, indexed by n. So there's 0 in the middle, and you have n copies around, and you have this span things in the middle. These are just to map them correctly to be a partial morphism. And usually then you can, if you have a category of graphs for using modal models, you can take a functor category. So you index over this diagram. And what you can say, these two ways of doing it are basically the same, but this one is basically just like a normal graph on the top. So there's some nice application of this functor theorem here that you have the third exponential law for functor categories for those people who know this. It's basically that the CS is that also reflects this partial morphisms. So the takeaway then as the practical application is, so now I have a tool to actually formalize this new world. So you can actually, the models with these rules on them, that will be the meta model. It's just one artifact. It's one of this comprehensive system thing. And it's basically just like a graph, what you had before. It only has these new things are these mappings in between that could relate elements, but it's just the same thing. Or basically, except for the mappings, because they are partial. And then below we have an instance that will be like all the local models together with the set of these traceability links combined in one artifact. And because this is a category, okay, you can again type it over this. So before you start, you look at your modeling languages that you have, and then you say, okay, there's a potential that you have this type of relationship between these concepts. And this will be then give you the structure. And in this structure, you can have you can define the traceability links that will be connecting. And that's all, yeah. So it's one nice theoretical tool to play around with. And then the question is it also useful? Because this is nice, but what can I do with it? So, and then that was we mainly did in these papers. There are some theoretical results for that. So first of all, it's in the world of category theory because this is the primary language where you work with this graph transformations. So that's the base, and there are some results that we built on. So one of these ideas is that functorial semantics is basically for databases. So when you have a category, you can interpret every node as a kind of set, and that will give you a database. So this is the indexed way of thinking about it. And then this is this is actually French. Wouldn't think there's an basically equivalent way of thinking about it, which is more aligned with how we think in model-driven engineering, that we have a graph structure that is typed over something instead of this is your schema and you interpret it via database tables. But these views are interchangeably via this. So, and then there's this thing of generalized sketches that we built about them, so which we needed to express predicates. And then there was also this idea that, okay, we can do consistency checking of multi-models via building a co-limit and then checking it there. And but this idea is basically much older. I think Gogen, and it's from the old guys, they have started with that. And then, of course, because we want to relate it to graph transformation, so that's all started with span categories, and then we have the algebraic graph transformation, the whole theoretical scope was started by Erik. So, and basically what you have there, when you have a category that is adhesive, then it's good, because that means you can do graph transformation. So, and this is some formal properties that you have to prove. So, yeah, and actually this was found out by other category theoreticians that found out that, oh yeah, what Erik and these guys are doing, you can summarize this really nicely abstractly. So, okay, so we had so new was we have just this definition, but a definition in its own is just yet another thing. So we proved also that you can think about as a local artifact, but it would be nice to have this adhesive properties, because that would mean we can do graph transformations. And it's not as easy, it's a like limited version of it. And what we did, we proved it by a theorem by hereditary push-outs. For those who know, that it's basically another characterization where you prove some certain other things. You prove that there are push-outs, and you say that they have this partial map classifiers, and that you have to, and this means you can do push-out rewriting. And all these proofs are found in these 3 papers. And almost of these proofs are diagram chasing, which is nice for people who like that. So some more other things to prove here, that we can also, that there are images, which means the pre-image functor has a right adjoint, which means we can do single push-out rewriting as well. That's a theoretical result, that was like a little bit homage to Pierre Löwe. And then finally, another property, that there are co-polarized initial objects, and that allows us to show that actually every time you have some kind of a category of graphs and you make this idea of a diagram, so you interpret a diagram in the graph category, which basically a triple graph is that. So you have a schema where you just have like 2 ends, the source, target, and something in between of them. and you interpret it as graphs. That this is also, it's just, you can think about a special case of comprehensive systems. That was one of the, so triple graphs are consumed, a little bit about us. So triple graphs is just a special case. The n is 2 and all the projections are total. So there was actually, I haven't mentioned it now, before, but now, there is something called graph diagrams that was Trollmann and Albayrak from Berlin. And they actually showed also, okay, you can think about of having more general diagrams. So you can say, okay, but they have to have a certain structure. So you can have different model types and different relation types that can also be ternary or binary. But the thing is, you have to fix all of that beforehand. While in comprehensive systems, you just say, oh yeah, I can support up to n, which n is arbitrary. And because you can always map any kind of this diagram to this general view where you have one apex in the middle and you have partial mappings between. So that was also showed in this. Yeah, and actually, because you have this weak adhesive HLR, you can think about it because these triple graph grammars are basically defined by means of graph grammars, which require this adhesiveness. You can define comprehensive system grammars. Could you think of how many systems together evolve? So that's theoretically possible. A little bit from the theoretical side, if people are interested, what is this M that I mentioned? Because we have this restriction of the adhesiveness to a certain type of morphisms, that they only exist along a certain type. So this is this reflective monomorphisms, and it basically means when you map between two, and you can, of course, always map. So if a projection is defined, it also has to define a target. But it doesn't have to be vice versa necessarily. So, but only if you require this reflectiveness. And for those who are doing algebra, that's basically, oh no, it's not close, it's fullness. That's fullness when you have it back. Yeah, so in CS, it looks like this, where usually this is an implication. If this becomes a bi-implication, you can also define this in this other way. There you say these inner diagrams are fullbacks. A practical example of this, what does it, if I think about rules? So if I want to do graph transformation rules for my comprehensive systems, and I, for example, map some systems where I have a relationship between three systems theoretically, and you have, and it says the rules are you map some sameness from one to another, you add an address somewhere between two things that are related. You can't not match this on a tentacle that has like, because this rule is only defined for two, you don't match this on tentacles that have more arms. Just one of these. There are more characterizations about this. And there's actually a related work by Jens Koziol and Gabi and collaborators that were looking into this, where these things, these pullback categories exist. But this is more, also can we think about, this is more stop more, where we don't require all the morphisms to have this reflectiveness, but only for the M part. So that's for the theory. Now, for summing it up, maybe something you get more applied again. So because the idea was, okay, now we have all these theoretical results, maybe we can also do something practical. And there were basically two branches. So one of this was a tool that we published in JOT at ESMFA at some point, where we had the idea, we had systems with GraphQL interfaces. So you actually have a schema that is a graph. And the idea was, okay, let's define like a correspondence between them, say what entities belong together, and then you do a federated system which puts all of them together, let them appear as one, and you merge the common parts together. So basically you co-limit, and you do translation of the data into one. So that was this tool. And also while we're doing the comprehensive system, we had a tool in Eclipse, and then, okay, maybe we can merge these two branches of development into something we called CorrLang. And I even bought a domain for it. So, and the idea is, okay, it's basically a DSL where you describe this intermodal relationship, and then you get basically for free this global system as one, which gives you the one endpoint interacting for your system. And it's basically loosely built on these theoretical ideas. So the first concept is you have something is called an endpoint, and there are two types of endpoints, which can be either servers or files. Black boxes or white boxes. A file, you can actually see the contents, so you see the model itself. While a black box, you can't see it by itself. You first have to send a message, and then you will get something back, but you will never see what's inside. but you can treat them kind of like in a similar way. And this is facilitated by something called a text-based plugin. So you can implement it for theoretically any technology by translating a concrete representation in technology to this graph idea. And there's two existing right now. There's GraphQL and EMF, eCore, facilitated via Epsilon, actually. Yeah. So, and every endpoint has a schema which defines the types, how they belong together, and some operations if it's a server. But you can also think about a file as a server by adding CRUD operations for everything. Yeah. So that's how you can align them if you have this heterogeneous space. So you have this. So every kind of server you have gives you a schema with the concepts, and you have the instance of them. And you can now, and formally they are represented as graphs, as I showed you, and graph morphisms, which are the mappings. These blue things in between where I draw the. Yeah. So how do I encode it formally? So this is something called this correspondence. And there's actually, yeah, the basic type is relate, where you say these two things somehow have a link, which basically allows you to reverse the links later. The identify is this idea you can also do the co-limit interpretation. You can merge things. And sync was this like a prototype where you can actually, where you have a relate, and basically you add this usual rule of they have to exist together. So that's like a synchronization constraints attached like in one as a language syntactic sugar. Yeah. And then, okay, you can think about these rules that you write here. That's the apex of the comprehensive system on the type level. So you have these two concepts. And then the last thing, you can write goals, where you can actually, you say, okay, refer to, and what you can do, you can either get you a schema of the whole thing together. You can get you a federation, which basically means you get schema and data, which then also can be a server running. So for the GraphQL world, it gets you one GraphQL server where you have aligned all the endpoints into one. And it does basically you send it a message and then it delegates messages to the Soker system and puts the responses together and types it under the new world. And you can do the verification with respect to the synchronization rules. Yeah. This is the big schema how to explains it. Yeah, so this is basically the language, how it looks like. There are some more concepts you can actually, there are keys when you want to identify data as well based on rules, because that's relatively fast. And there's also a way where you can actually plug in, so because you always construct this global artifact, so you can also actually delegate this over to some existing technology like Epsilon, and then run the check in Epsilon and get the result back with something called rules. That is a bit more experimental feature, I would say. So there's actually a video, because I think it's a bit short on time, so which shows it very nicely. I will upload the presentation later too, so you can watch it at home. Basically, maybe it's better. So what you can basically see here is first, you see that there are different, 3 different systems where you identify they have different schemas, which are visualized using plant UML. And then what happens afterwards is that in this DSL, we add these rules that say identify some stuff. And then it merges together this one concept, this partner, which is basically a customer and everyone into one. Watch that, and then in the end you run the whole system, which then fetches data from all the endpoints into one where they have. So that was a bit quick, but you can watch the video maybe later if you're interested. Yes, which brings me to the related work part. So what is related, which I mean, I have covered a lot of background. So there are some things that I didn't expressly mention, but I think it's interesting to mention now. Semantic Web has thought about this very much, and they actually use a similar representation because in Semantic Web, everything is a graph, but they all put it down on one level, and then they want to do reasoning on the other. Whereas here is more the focus on mediation, ad hoc mediation. And then all of this work on extract transformation load or extract load transformation is similar idea because you have multiple heterogeneous data sources with different formats and you want to extract them. But here the focus is more like you have many and then you put it into one data warehouse. Whereas this tool is more like many to many and you have not this from operation to analytical, but you have operational systems communicating. And then I don't know if you know it, there's this word on GReTA, of course, you know, there was this talk by Ryan Wisniewski and CQL, the category query language. It's quite very similar ideas. They have a little bit the focus there. They have this database, this index semantics view, whereas here is more, and the focus is just on this query part. Here's the focus was more on graph transformation and type structures. Yeah, and of course, there's more ideas for future work. On the theory, there's this whole world of comprehensive system grammars. How do they actually would look like? Because in general, it would be cumbersome to write them, but maybe you can automatically look at them. What are the interesting splitting of these rules? Because that's what's basically doing triple graph grammars. You say all of it, and you can have different types of splittings, which give you these propagations. In comprehensive systems, because you have this much more wider span, you have many more ways of splitting them. Then this whole idea of what we need as modelers in the formal world, we want to have attributes where you have these data types. We want to usually also have something called inheritance. And now we had commonalities, which and all of this is something, a same instance of the same thing. So if you look in this world, when you look in this, the world by Wisniewski and Spivak in this algebraic databases, they basically, you have the schema and you map it into a set, the database, and you sometimes, some of the nodes you interpret as data schema, so basically an algebra, which is basically a special case of something called a profunctor. And also, what we have seen here, now the comprehensive systems was just so special. It looks like this, actually. You have the schema of your structure, and you have the schema of your spans, and both of them are also something. And then also, what would we, if we do the schema, like the syntactical schema with itself, maybe that gives us an idea of inheritance. So that's some ideas, but they have to go more through. Then how the whole idea, okay, if I make some comprehensive systems and then make comprehensive systems of comprehensive systems, so then I maybe can get to some idea, like in the internet, you do this many levels and how does it work by propagating back, up and down? Yeah. So on the theory side, and then on practice level, there's more to do. Of course, it would be nice to have text-based adapters to everything for Open API, gRPC, SQL, Avo, and so on, to use it in practice. Use cases to apply it to actually see if it's somehow stands the test in the real world. And then, of course, it needs more tooling because it's just writing it down in text editor and the command line. But that's also robust. You don't have to install Eclipse. So in some sense, yes. Oh, yeah, there's a lot of references. But then, yeah, I guess that's 40 minutes. I stop here, and then I leave some time for questions. But also Nick, I guess, can see what's written in the chat. But if there's a question coming through here, I will through the. Yes, then I repeat it. Yes, yeah, yes.
Can you hear me? Is it possible to ask?
Yep.
Ask
Yes, yes,
okay?
yeah.
Okay, so yeah, over here. I'm just trying to understand, in particular, the role of the partial functions there, or the partial morphisms, whatever they are, because that part was just.
There's one question coming online right now. So the question was, what is the role of the partial mappings, right?
Yeah.
Heiko?
So the reason I'm asking is that something which is sort of vaguely related, even if it's not the same in terms of motivation. There's a notion of distributed graphs by Gabi Tänzer from a few years ago, and so there's a diagram over the category of graphs, which has basically graphs and relationships between graphs and sort of interfaces and so on. is not done from the point of view of model management, but more from the point of view of modeling distributed systems, as you probably know. But there's also there a distinction between a variant that has total morphisms only and a variant that has partial morphisms.
Yeah. So there
And
was
partial
now a
morphisms
question about the
represent-
role of the partial morphisms, because this relates to work of GReTA and collaborators. I will show maybe get this where you have basically these ideas of a diagram of relationships where you distinguish between total and partial. Now I don't have exactly the paper from Gabi in my head right now, so just I start with this one here maybe. So the role of the partial map is basically because I don't want to spend too much time before I'm thinking about what are the possible relationships I can express between my models. I want to have like one general ambient where I can do theoretically everything, and that has like one parameter, that's the n, the maximum number of models I can possibly integrate. And the idea is I set it pretty high, and then it's good. And then I'm gather together all possible relations into one, that they are all gathered in the center. And then I have the partial mappings are then used to express basically the relations. And the idea is, okay, when I have this ambient that much generic, because that would be probably something that will be glued into the tool that is not changeable. But then what the modeler is doing, he will then have the freedom to define this thing in the middle. What are the possible relationship types? Because he knows the schema. And then he will basically set a narrower context of what is allowed. So, and I guess that one, the work of Gabi would be much more in this world of the graph diagrams from Albayrak and so on. I guess that's then a more refined version where you actually have this distinction between the total and the partial ones. Baked into here, because that one in the graph diagrams world, there's basically everything is total. So
what Gabi does,
you can always translate every graph diagram into this more general thing by just collecting everything into the apex.
So the total.
Then also there's this theory link by this paper 24. That's the last thing I know, where they have this they call it Cartesian morphisms, where they investigate adhesivity on that level. Does that answer the question, Raiko?
Yes, in principle. In the sense that you have partiality because you want to be flexible and you don't want to force
beforehand
force complete consistency essentially from the beginning.
Yes.
Because it emerges in the process rather than being given upfront.
Yeah, and because you can basically and the idea is that because you can actually put diagrams also on the projections, they are just as normal edges, you could actually encode totality as a predicate. So if you want to have that, the modeler can do that by putting the constraint on it. But the general ambient would be the allow everything.
Okay. Yeah, thank you.
Yes, they are finished. So there's a question by Adrian. This one? Oh, this one. Yeah. Yeah, so, and for the virtual audience, so there was a remark and a question by Adrian, because there was earlier here was a talk also about a similar idea actually with the federation. So you have links between elements from different models and you can relate them. And here you have a way of typing them. So now the question is what the typings mean. What's the type of the type? So this would be the top level. So what's the type of this? And what would these things be typed? Well, all of this would be typed in this B thing that I showed earlier. That in this case it would be an E graph, but it could be also directed graph. So that's this there's the other parameter. So there's two parameters. You have this n, maximum amount of models you can integrate, and you have the b, that would be the syntactic base, what you can express your models in. And usually this is some sort of graph, because in software most things are somehow a graph. Yeah, it would be the Yeah, I think so, because it's the similar concepts, because you have models and you have links between model elements. Yeah. The thing that is a bit different between, okay, the question was this talk on FML, but I can't repeat the whole talk on FM. So yeah, yeah. So the new thing is that you basically have this ambient that you have this typing, right? So that's something that is a bit different. So you have this idea, okay, I first also have to define a type of possible relationships before I can start tracing on the law. Yeah. But I guess, yeah. Another one. Which one? Yeah. Oh yeah, yeah. The new that would be just the name for the global thing. Yeah, which are systems. That's the name of the schema, basically. Yeah. So the question was, what does it? Yeah. What? Yeah, so the question was here, what is it possible to define types between, basically, when you're using this three, the syntactic elements, relate, sync, identify. And what you basically put in the parenthesis is the name of elements in that individual schemas, which basically are induced by defining endpoints. And then the text-based adapter will identify what is the schema behind that for that system, which will give you the meta model graph, basically. And what you can put here is basically an element that is identifiable in the meta model graph. So if this is something that doesn't exist, you get a syntax error. Yeah, and they also have to. You can't identify edges and nodes, for example. Yeah. Yeah. Mm. Thanks. Yes. So we thank the audience and the apparatus at home. Yeah, I should say.
Okay, thank you very much.
So yeah.
All right, so thanks everyone online. We will now wrap up the session, and we will see you all in the new year on January 12th, where the talk will be about the RET project, so hypergraph rewriting and such. So thanks everyone who was online. Sorry for the slight technical difficulties. Yes, Reike, do you want to add anything?
No, just say, yeah, have a good Christmas, and we see you all in the new year. Thank you, and thank you for managing all of this, even difficult circumstances here.
Yeah. Well, greetings from Paris, and until soon.